Yes. Yes. Screen is visible to all of you.
Yes, ma'am.
Yes. Okay. Yesterday, some students might have drive. Okay, GMS. Okay. So that some students are absent for that session yesterday. Okay. So that I will revise heat temperature. Heat balance equation. That is temperature rise of conductors and current carrying capacity. The screen is visible or not? Yes. Yes. Screen is visible. Yes. Anyone? Screen is visible. Yes. Screen is visible or not?
Yes,
The,
ma'am. Visible.
okay. Okay. Yesterday we have seen temperature rise of conductors and current carrying capacity. Okay. I will revise uh, for those students who have drive yesterday. Okay. What is meant by current carrying capacity and some equations to calculate the heat balance. Okay. Yes. All of you are getting. Yes.
Yes, madam.
Okay. Okay. Let's start this session. Okay. Uh, Means we are going to see temperature rise of conductors. What is the temperature rise of bundled conductors and what is meant by current carrying capacity. Okay. Uh, Current carrying capacity is nothing but how much of means we can say maximum current that continuously passes through that conductor without any excess of uh, or develop of heat. Okay, we can say maximum current that flows through that conducting material without causing of excess heat. Okay, yesterday we have seen this heat balance equation. We are going to see again when a conductor is carrying current, its temperature has reached a steady state value. Heat balance requires this is a heat balance equation we are going to see. Means once conductor attains a steady state value of temperature, then how we are going to calculate heat equation. Okay, how we are going to calculate how much of heat is going to be developed. Here we are going to see in 3.8 equation. Okay. Next, heat balance equation requires this internal heat developed by I square R plus external heat supplied by solar irradiation is equal to heat lost by convection to air plus heat lost by radiation. Okay. All of you know I square R means what? Means flow of current through that resistor. Okay, through that resistance. Okay, I square R loss. Next, solar irradiation means which is related to solar wavelength. Okay, and next convection is nothing but the process of that material to means conversion from that material to air or water. Okay, heat lost by radiation. This is a again related to solar system. Okay, radiation means um, how much of area is going to be heated with the help of or by sun. Okay, all of you are getting this 3.8 equation. Okay, uh, means if we are going to write this 3-point equation, it is a lengthy, so that we are going to assign these separate terms various notations. Okay, so that it will be easy to write 3.8 equations. So we are going to suppose or letting these terms for some notations. Okay, you are going to see this wi. Okay, we are going to assign this Wi to internal heat developed by I square R. Okay, this is I square R heating in watts per meter length of conductor. We are going to take. Okay, now this Ws is nothing but solar radiation. Solar irradiations supplied means watts per meter length of conductor, and Wc is convection loss, which is also given in watts per meter of length of conductor. And next Wr, radiation loss. Okay, this is a Wr. This is the last term of 3.8 equation we are going to take. Okay, by putting these notations in equation 3.8, we get one equation, that is heat balance equation. Okay, this is nothing but heat balance equation by assigning the notation for that 3.8 equation, previous equation we can say. Okay, by putting the supposed notations, okay, we get heat balance equation as Wi plus Ws is equal to Wc plus Wr. This equation we get by assigning the notations. Okay, now these terms we can see, all of you are going to see this 3.9 equation. Yes, all of you are visible. Yes, each of these four terms depends on several factors which must be written out in terms of temperature. Okay, okay, means we are going to see these four terms Wi, Ws, Wc and Wr are depends on several factors which we can say, that is temperature, conductor dimensions, wind velocity, atmospheric pressure, current, resistance. Okay, then conductor surface condition, etc. Means these four terms of 3.9 equation, that is heat balance equations, are depends on these various factors. Okay, in MCQ type of question, if offline exam is there, then there is no worry to objective questions. Okay, as exams are going to be offline, so we have to put these all factors for this heat balance equation. Okay, on which factors these four terms are mostly dependent. Okay, it will then be possible to find a relation between temperature rise and current, so that we can see current and temperature rise relation. Okay, we are going to see what is the formula to calculate this Wi, Ws, Wc and Wr, so that we can calculate these four terms, and after that we got one relationship between temperature rise and current. Okay, all of you are getting why this equation is taking here. Yes. Yes, firstly, point our we are taking temperature rise of conductors and current carrying capacity. So obviously, this heat balance equations relates to temperature rise and current. Okay, all of you are getting? Yes, yes, all of you are getting. I am taking revision. Okay, already yesterday these parts has done. Okay. Now this is visible. Visible. This heat balance equation. Yes. Yes. This is okay. Please tell if slide is not visible to all. Okay. You are only listening then my voice. No one is going to concentrate on this heat balance equation. Okay. All need is for me as a teacher. Okay. No student is seriously involved in these lectures. Okay. If exams are going to be offline, then you can see how this subject is actually. Okay. Now this heat balance equation becomes, by assigning these notations, this temperature, we will get relationship between temperature rise and current. Okay. Now we are going to see what is the maximum allowable temperature for the various conductors. Okay. For aluminum, it is going to be 65 degrees Celsius, but it will be increased up to, it will be increased up to 75 degrees Celsius. Okay. Many countries in the world have already specified the limit as 75 degrees Celsius, above which the metal loses its tensile strength. Okay. Means after 70, we can see some materials have low tensile strength, so that as the temperature increases, it tensile strength that they loses. Okay, how much they bear, which is the strength of that material. Okay, the four quantities given above are as follows. Means these four quantities we are going to see actually. This I square R heating is visible. First point, screen is visible. Yes, yes. Ankita, screen is visible. There is Shraddha. Yes, screen is visible or not? Yes.
Visible.
Okay. Now we are going to see this heat balance equation, how we are going to actually calculate. Okay. Firstly, we are going to see what is I square R heating formula. Okay, which is nothing but WI. I square RM watts per meter, where RM is resistance of conductor per meter length of at maximum temperature. This is the resistance RM of that conductor per meter length for the maximum temperature. This formula is Rm is equal to 1 plus alpha T divided by 1 plus 20 alpha into R20. Okay, they have taken uh, this resistance at 20 degrees Celsius. So they have taken in this equation as a 20. As per given in example, we can take here, if we are going to take this 30 degrees Celsius temperature, we have to put here as a 30. Okay, for here subscript of R, we are going to put as 30 also. All of you are getting? Yes. Yes. All of you are getting? Okay. Now, this alpha is a temperature resistance coefficient in ohm per degree Celsius, and R20 is the conductor resistance at 20 degrees Celsius. Okay. Now, next term is solar irradiation, which is Ws is equal to SA into Is into dm. These terms also is given in watts per meter. So dm is the diameter of conductor in meter. SA is the solar absorption coefficient. This vary for various we can say bodies of that conductor. Okay, one for black body or well weathered conductor, or and 0.6 for new conductor. Okay, this coefficient means SA. This varies according to the body of that conductor, or we have taken new or a black body or a well weathered conductor. This coefficient depends on that. Okay, as per given in example, we have to take this coefficient. Okay, if in some example they have taken new conductor, you have to put say 0.6, and if for black body or well weathered conductor, you have to put it as 1. Okay, and Is is solar irradiation intensity in watts per meter square. Okay, already I have told you what is meant by solar irradiation. Okay, that would be measured in watts per meter square. Okay, this they have taken some values at various places. At New Delhi in summer days at noon, it has a value approximately up to 1000 to 1500 watts per meter. And what is the calories square centimeter per day also given. This is for general they have given. Okay, now this is a convection loss. All of you are seeing this convection loss. Why students are leaving? Only 28 participants are there. 4 participants have leave the meet. Okay, I have taken roll number of them. Okay, those who have joined and they leave the meet, I will put absentee for them. Okay, this revision session is not for me. Okay, those who have joined. Okay, I am not allowing this roll number 13. Okay, please tell her to not to join the meet. Okay, firstly she has joined the session and again leaving the session. Okay, what are you doing now? Okay, only I have this work to admit the students. You can live by your own way. Okay, this revision session is not for me. Okay, already I have taken this point yesterday. If you are not taking seriously, then I am going to take this seriously. Okay, if you are very talented students, you can take these subjects by your own. Okay, I'm seeing previously 33 students are present. Okay, now 20, 28, 29. Okay, why I'm then revising this all of you? Okay. If classes are going to be offline, I will revise this from students only. Okay, which what points I have taken during online lectures. Okay, this is now 2:30 is there, and some students are joining the meet. Okay, tell them to not to join. Screen is visible or not? Connection loss. Yes, at least you can give response. I'm not giving marks for you for that, or I'm not giving you negative marks for that, for yes or no answer. Yes, roll number 13. Roll number 13. Who is roll number 13? Roll number 10. 9. Roll number 9. Who is roll number 9? Okay, I will see now. Who is roll number 9? 9. I think he or she. Wait. Acha, Vaishnavi Dhole is there. Okay, I am taken randomly these numbers. Okay, where is Vaishnavi? Yes, Vaishnavi, where are you? Yes, okay, yes, yes. My voice is not audible to all of you. Yes, okay, Vaishnavi, okay. You are going to be mute. Okay, you can tell. Yes, you can unmute yourself by your phone. Yes, yes. Where is Vaishnavi? Yes, she is going to tell now what we have seen from first lecture. Yes, where is she? Okay, call her. Anyone from girls? Okay, she is going to tell today. Okay, so I have muted all of you. Yes, now see. Yes, now. Yes. Okay, no one again. No one is responding. You can now. Now you can. Yes. Please now check. I will check. Now see, you can speak by unmuting yourself. See, yes, is there? Yes, same issue. Okay. Okay, you can put in chat box also. Okay, if there is any issue for unmuting. Okay, tell me what is heat balance equation. Tell me what is heat balance equation. There is a rule number 9. You can put in chat box so that everyone can see. Yes? See, again, okay, I will. Yes, where is the roll number? We, where is Pratidnya? She has joined. Where, Pratidnya? Yes, Pratidnya. I'm audible to you. Yes, yes. Okay, I think if students are only listening, then my work is also to listen you. Okay, I'm also keeping myself silent. Okay, now one student will tell from first lecture what we have seen. Okay, yes, roll number 9. I'm going to ask you 18. Where roll number is 18 is there? Okay, 27 is there? Yes. In multiples of 9, I'm taking. Okay, tell. In multiples of 9. Yes. 9. What is the heat balance equation? Yes. Yes. Screen is visible or not? Is my screen is visible or not? Yes. You can put in chat box. I'm not going to give you marks for that. Yes. Yes, please. Yes. Visible. Okay, Kishore sound. Okay, screen is visible. You can put this 3.9 formula as it is. Okay. Yes. Okay, next. This is a this I square R heating formula, and this is a solar irradiations. We have taken notation as WS for this solar irradiation, and for I square R heating, we have taken it as RM. Okay, this is a formulas to calculate I square R heating and solar irradiation. Okay, these two formulas. Okay, we are going to substitute in 3.9 equations again. So see this. Third is convection loss. That is WC. This is 5.373 into small p Vm divided by dm into delta t. That's per meter square. Okay. This is a formula for the convection loss, where P is the pressure of air in atmosphere, Vm is wind velocity in meter per second, and delta T is temperature rise in degree Celsius above ambient temperatures, which is T minus TA into P Vm dm. Okay, this is a delta T formula. This is screen is visible. T minus TA PVM dm, since 1 meter length of conductor has an area, P into dm means here pressure of air and dm is the diameter of that conductor in square meter. The convection loss is given by, okay, WC is equal to 18 into delta T under root of small p into Vm into dm watts per meter. This formula is for convection loss. Okay, now radiation loss. This is given by Stefan-Boltzmann law. Okay, which is given by WR is equal to 5.702 into 10 raised to minus 8 E into T raised to 4 minus TA raised to 4, which is in watts per meter, where E is the relative emissivity of conductor surface, which is one for, again this is also we can say one coefficient related to that loss. Okay, again it is for black body, it is a 1, and for oxidized for it is 0.5 or Cu. Okay, this material is also given for Cu, it is a 0.5, and T is a conductor temperature in Kelvin, which is given as 273 plus T, and Ta is the ambient temperature. Okay, what is meant by ambient temperature? What is meant by ambient temperature? Already I have told you. Screen is visible for this radiation loss. Yes, screen is visible for this. Yes, please. You can put simply yes if it is visible. Yes. Okay. I am going next, but some students or all students not visible slide, so I am asking you these questions again and again. Yes. Yes. Yes, you can put in chat box visible. Okay. Now this is a ambient temperature, which is a at this is a maximum temperature at which that equipment is stored for that temperature. Okay, that is the ambient temperature, which is in Kelvin, given by 273 plus Ta. Okay, this is in watts per meter. We have to take this watts per meter in watts per cent. Sorry, watts per meter square in watt per meter, so that all terms will be of same unit. Okay, this is a radiation loss per meter length of conductor is WR is equal to 17.9 into 10 raised to minus 8 E into T raised to 4 minus TA4 into dm, which is in watts per meter. Now we have to put these four equations in 3.9, so that we get heat balance equation as I square Rm plus SA ISTM is equal to 18 into delta T under root of small p into Vm under root of dm plus 17.9 into dm of t divided by 100 minus t raised to 4 divided by 100 in square bracket. Okay, all of you are getting this? Yes? Yes? T raised to 4 है बड़ा. Yes? This is a Stephen-Boltzmann law we have taken. Okay, now we are going to see what are the properties of bundle conductors. Yes, yes, this slide is visible. Yes, yes. Anyone? Okay. Now we are going to see what are the properties of bundle conductors. Okay. Uh, we have seen also various conductors that we can see standard conductors. We have seen in first lecture. Okay, which conductors we have seen, that is triple AC, ACSR conductors. Okay, means bundle conductors are exclusively used for extra high voltage transmission lines. Okay, these bundle conductors are used for this extra high voltage transmission lines. Only one line in the world, that of Bonneville Power Administration in the USA, has used a special expanded ACSR conductor of 2.5 inch diameter for their 525 kV line. Okay, this is a this administration has used diameter of 2.5 inch for their 525 kV line. Okay, this is a conductor size they have used. Okay, we are going to see what type of configurations they have used for the bundle conductors. Okay, this we can see conductor configurations used for bundles in extra high voltage lines. Okay, this is a single conductor configuration. This is a twin. This is a three conductor. This is a four conductor, six and eight conductor. Okay, now as of maximally for experimental lines, they have taken 18 subconductors, but for commercial lines, 8 conductors have been used for lines of 1150 kV to 1200 kV. Okay, these configurations have used, you can see. Yes, yesterday I have also used this, means I have taken this point. Okay, and this part is new for all of you, that is bundle spacing and bundle radius. What is it? Okay, all of you are going to see this slide. Yes, yes, all of you are going to see this slide. Yes, please. Yes, yes, you can visible. Yes, please, so that I will take this part. Okay, now what means I have only taken this properties of bundle conductors and I have stopped up to this configurations. Now we are going to see which properties are there for the bundle conductors. Okay. In that, we are going to see bundle spacing and bundle radius, or we can say diameter. In almost all cases, the subconductors of a bundle are uniformly distributed on a circle of radius r. We can see subconductor of a bundle are uniformly distributed. Okay, means for we can say for space. Okay, they are uniformly distributed. Okay, of circle radius r. They are proposals to space them non-uniformly to lower the audible noise generated by the bundle conductors. Okay, already we have seen what types of mechanical considerations and noises are there in third lecture. Okay, but we will develop the relevant geometrical properties of an n conductor bundle on assumption of uniform spacing of the subconductors. We can see this bundle spacing B and bundle radius R. All of you are going to see this figure. Yes, all of you are going to see this figure. Yes, yes, please. You can give response. It is also reported that the flashover voltage of a long air gap is increased when a non-uniform spacing for subconductors is used for the phase conductor. Okay, means we have seen flashover voltage is there if when there is a non-uniform spacing of some conductors used for the phase conductor. Okay, this is a bundle spacing and bundle radius r. Here we can see figure 3.4 is visible. Yes, figure 3.4 is visible. Three point four figure is visible to all of you. Yes, please, you can tell so that I will go to next paragraph. Yes. Okay. I'm considering 3.4 is visible to all of you. Yes. Yes, please. Okay. The spacing between adjacent subconductors is termed bundle spacing. Here we can see B. This is a bundle spacing, which is a spacing between two adjacent subconductors. Okay, all of you are going to see this. B. Yes. Please give response. Yes, please. Okay, and it is denoted by B. So bundle spacing is capital B. Okay, the radius of each circle on which the subconductors are located will be called as bundle radius. Okay, here this is the radius on which subconductors are located. Here we can see the bundle radius R. It is denoted by R. The radius of each subconductor is R with diameter D. The angle subtended at the center by adjacent subconductor is, this is 2 pi by n radians. Okay, this is the angle. Okay, 2 pi by n. between 1 and 2 subconductors. Here we can see they have given 2 pi by n angle which is in radians. Next for 2 to 3 this is it is going to be 4 pi by n. Yes, all of you are going to see this. Yes, and it is readily seen that b by 2 means here bundle spacing b by 2 is equal to r into sine pi by n and giving r, okay, b by 2 sine of pi by n. This is the 3.11 equation. Yes, yes, all of you are getting this. This is the standard equations they have given. Yes, 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 please. This screen is visible to all of you or not? Bundle spacing and bundle radius. Yes, yes, please. Yes, yes. Can you put in chat box this equation for bundle spacing and radius? Yes. For okay. This is the bundle spacing and radius property of that bundle conductor. Next, for number of conductors from 2 to 18, the following table gives R to means R by B to B by R. Okay, from this equation, okay, this here we can see R by B and B by R. Here we can take from this equation. Okay, all of you are going to see by putting value of R n here. Okay, we are going to see this R by B and B by R. Okay, all of you are getting this. Okay, you can calculate. Okay. Please, if anyone have this calculator, you can calculate B by 2 R sine pi by 2. Okay, we can take what is sine pi by 2. Yes, sine pi by 2. Sine pi by 2. Yes, what is the value of sine pi by 2? 0. Sine pi by 2 is 0. 1. Again, which sine pi by 2? 1. Okay, we simply put this value in. If we take n as 2, you have to put this value of n in this 3.9 equation. If b by 2 is equal to r into sine pi by 2 is there. Next, b by 2 is equal to r sine pi by 2 is 1. So b by r we get as 2. All of you are getting this. Okay, b by r. Okay, here we get 2. All of you are getting. Yes, all of you are getting how this b by r came. Okay, again for this r by b, simply we have to take B is equal to 2R, so that R by B is 1 by 2 means 0.5. All of you are getting how these values are going to be calculated. Okay, how bundle spacing and bundle radius. Yes, you can calculate. I have taken for n is equal to 2. If we have time, you can see how this values comes. Okay, yes, yes, you can see. Yes. All of you are getting this table, how comes? Okay, I have taken one calculation for n is equal to 2. If we put 3 pi sin pi by of 3, you have to take, and by rearranging the value or by rearranging the b and r, we get the ratio this r by b and b by r. All of you are getting? Yes, all of you are getting? All of you are getting this? How comes? You can calculate also. Okay, next geometric mean radius of bundle. Previously we have taken bundle spacing and bundle radius. Okay, now we are going to see geometric mean radius. Okay, I think 3 is there. You can, okay, anyone has doubt? Yes, anyone has doubt?